Hi, I'm Majid Aliri. I want to present the efficient approximation for cache conscious data placement paper that was accepted to the PLDI 2022. That was a joint work with collaboration with Professor Gohar Shadi from HKUST, Professor Pavlogenius from Ahris University, and me and Ali Ahmadi from Tehran, me from University of Tehran, and Ali from University of Sharif. Uh, the cache conscious data placement, or CDP, is a classical problem that was introduced by Calder in S Plus conference in 1998. Uh, Consider a memory system consisting of main memory that is huge but slow, and a small cache that is fast. Uh, and when a program want to access an object O, if the object is in cache, the access is successful or hit, and otherwise we have a cache miss, and O has to be copied from the memory to the cache. Uh, Assume that we are given a sequence of access. Our goal to minimize the cache misses over sigma, that is the access sequence. We have, for example, we have an object. We can assume that they are O1 to ON, and sigma, as discussed, is the access sequence of these items, and the cache consists of k lines, and initially it's empty. Each line can hold up to t item at any time. In this talk, we are going to the t equal 1, but our algorithm works for any t. Each item O has a dedicated line of f, f of I, and we call this f function a placement map. And we are going to find an optimal placement that minimize the number of cache misses, and we analyze the runtime based on n and capital N, and assume that t and k are small constants. We have a theorem that was proved by Petrank and Rabbit in Popple 2002, uh, that that they have proved that for a cache with more than two line, CDP is not only MP hard, but also hard to approximate within any non-trivial factor, unless P equal MP. This is very strong hardness result, and all following works were heuristic with no guarantee or theoretical guarantee. Uh, and we were the first positive theoretical result for CDP, and our algorithm works based on the sparsity of access graph, and we design a linear time 1 plus epsilon approximation for optimal number of cache misses, assuming that access graph of some specific degree is sparse, and sparse instances lead us to a better approximation. Uh, both uh, and we have also proved that both approximation and parameterization is are needed at same time, and you can refer to paper for seeing the details of uh, these proof. And we have some experimental result, uh, and on, for example, some small cache, our approach beat the heuristic for 8 84 to 88% of cases. And you can also refer to a paper to see the experimental results. And uh, let's go through the algorithm. Uh, for example, we have the sequence of sigma, and we then construct the axis graph. As we see, each element connect to an element that come after each item. For example, O1 come after O3, so we connect O3 to O1. And our basic idea was, if, for example, we are accessing some item OI, and the previous access to this object OI was far, far from now. So we can assume that uh, this may not presented in the cache, and we can assume that current access is a cache miss, and we should, for example, we should get the object from the main memory. And obviously the first access to OI, because the cache is empty at first time, uh, is also a miss. And and if this is the first access to OI, or we have seen at least the distinct item uh, since the last access to OI, then we assume a cache misses happen. For example, we can see on this example, assume that the sigma is the access sequence and d is equal to 3. So we have O1 for axis 1 at the first axis, E2 for the second, and E3 for the third, and etc. So as we imply, because E1 and E2 is the first access to O1 and O2, we assume they are the cache misses. And because the O4 is also um, the first access, E4 is the first access to O4, we can also assume that as a cache miss. If E5 is similar, and E6, because uh, this is also a first access to E03, is also a cache misses. E8 uh, is the case that the access the the distance between uh, two axes to O1 is more than D, so we can assume that E8 uh, has a cache miss. So we have a theorem that for any epsilon greater than 0, by applying the approach uh, using the sparsified hypergraph uh, of order d equal uh, the described equation, we obtain a 1 plus epsilon approximation of optimal number of cache misses in direct mapped cache. And we have this formulate that can our placement that is f hat is and assume that f star is the optimal uh, data placement policy. So we have the 1 plus epsilon approximation on this. Uh, Graph coloring. Every edge in our hypergraph starts and ends with the same vertex. A placement map is basically a color of this hypergraph with k color. Uh, Remember that k is the number of cache lines. An edge corresponding to a cache miss. If the color assigned to its endpoint is reused in its middle as well. And the MP hard problem is to find a coloring that minimize the missed edges. Um, we assume our sparsified axis graph have small treewidths, uh, and we can refer for that to a paper that was published in Popl 2019, uh, Chatterjee et al. Uh, do a linear time bottom-up dynamic algorithm as if we are coloring a tree. We have a simple DP dynamic programming that for each BI and partitional coloring C that find the number of minimum cache misses or missed edge in subtree of BI. If the color of the vertices in BI is according to C. Uh, that can solve our problem, and then we can count the uh, missing edge, and they are corresponding to the cache misses. So at the conclusion, we can anyone that listen to this video can draw a conclusion that CDP is very hard, and even the access sequence is given. It is hard. It's not as hard as previously thought, since real problem instances are sparse. The sparsity can be exploited to obtain 1 plus epsilon approximation, and CDP requires both approximation and parameterization to become tractable. And we provide the first positive theoretical result for CDP, but there is still a long way until it becomes practical. And the current algorithm can be used for limit studies and comparison of heuristics. Thank you for listening.
You mentioned that this work mainly focuses single-threaded program. So, how do you think you could uh, extend this to like multi-threaded programs, and what are the challenges that you have?
So I don't think there is a straightforward extension of this work to multi-threaded programs. The main challenge is that we are working in the offline case where we know the sequence of accesses beforehand. And so the problem was theoretically hard even in this case. And so adding multi-threading makes it so that we can have many different sequences. And so basically our approach would not be applicable in that case at all.
Okay. All right. So I have a question from Hassan. So, I mean, what is the main hurdle until this algorithm is applicable in real world situations?
So the main hurdle seems to be that right now we could find an algorithm that basically pushes all the complexity on the cache size. So now our algorithm is linear time in terms of the number of data items in the memory and also the length of the sequence, but we've pushed all the complexity on the cache size. And so the dependence is currently exponential, but there is no reason why it should be like this. And if you can somehow decrease the dependence on the size of the cache, then it would be applicable for more real-world cases. But again, from a theoretical point of view, what we were trying to prove here was that the algorithm becomes fixed parameter tractable. And for fixed parameter tractability, we used the cache size as our parameter. So we usually do not care about theoretically do not care about the dependence on the parameter.
All right. So I think we are almost out of time for questions. Please talk. So thank you, Amir, again for answering questions.